Hello everyone, my name is Montu, and I'm going to be talking about my Caltech SURF project that I did this summer. So my Caltech SURF project that I did this summer was Astrophotonics, or more specifically, the simulation of astronomical spectroscopy with photonic spectrographs. So my mentors were Dr. Gutkin, Dr. Jovanovic, and Dr. Mawit, who have helped guide me and supervise this project. So in this presentation, I'm going to be talking about astrophotonics, what astrophotonics is, my contributions to the project dealing with arrayed waveguide gratings, low resolution, high resolution spectrographs, and regularization and spectral shifts. So what is the motivation behind this research project? What is the inspiration for the type of contributions that I made to the project and what we were able to do this summer? So as we know, astronomy is moving towards detecting and characterizing exoplanets. So typical astronomical telescopes are detecting telescopes that pass in front of their parent star through transiting, or gravitational wobbling through the Doppler effect, or direct imaging, and being able to characterize these exoplanets, such as using spectroscopy to find the chemical composition of these exoplanets, the chemical composition of the atmospheres, so that way we can determine what creates and what is the cause of life on planets, and see if other exoplanets have life just like ours. So typical telescopes use conventional bulk optic spectrographs. These bulk optic spectrographs are actually proportional to the sizes of these telescopes. However, the main problem with bulk optic spectrographs is that they're difficult to maintain thermal and mechanical stability for precision spectroscopy. This is where astrophotonics comes in. Astrophotonics can help by making compact spectrographs for both ground and space telescopes. So creating compact spectrographs is very useful for space telescopes to more efficiently be able to characterize these exoplanets. So first off, what is astrophotonics? Astrophotonics deals with guiding light in single mode optical waveguides. So in order to understand what a single mode optical waveguide is, take a look at the diagram on the left. This deals with light propagating through a light pipe. So the light is propagating through a light pipe, and on the right you will see the single mode optical waveguide. Essentially, light is propagating through this waveguide with different mediums such as silicon nitride and silicon dioxide. Um, doing such will help perform precise operations such as spectroscopy, interferometry, filtering, and more. So that's what the aim of astrophotonics and guiding light in along these waveguides is, to help with operations such as spectroscopy, which is what we're mainly dealing with. We also aim to build instruments on a chip for future astronomical telescopes, which is very useful for better efficiency to better characterize these exoplanets. And these miniaturized instruments allow applications that are not possible with conventional bulk optics. And using arrayed waveguide gratings is actually one of the most promising ways to perform spectroscopy using astrophotonics. Or other words for arrayed waveguide gratings is AWGs. So first off, what are arrayed waveguide gratings and how do they work? So an arrayed waveguide grating works as such. You have an input beam of photons through a waveguide. The beam of photons will propagate through the waveguide, very similar to how photons will propagate through an optical fiber through total internal reflection. If you have a certain medium with one index and an outside medium with a lower index of refraction, and it surpasses a critical angle, the light will propagate through the optical fiber through total internal reflection. Similarly, it'll propagate through the waveguide very similarly to total internal reflection. So as it propagates through the waveguide, there's a free propagation region which will split the light into corresponding waveguides, creating an array of waveguides. And this arrayed waveguide has light of different wavelengths. However, now there'll be a path difference created. There's a path difference. There's a path difference between the waveguides. So it'll diffract and the light will constructively interfere, and thus you'll have an output spectrum. Each waveguide, you'll have an output spectrum. So the spectrum is a result of a path difference in waveguides, which will lead to constructive interference. So thus the output is a spectrum. Our AWG is constructed for transverse electric polarization. So what we dealt with was simulating AWG response. So what we did was we simulated the throughput from AWG response at each channel. To better explain what we mean here, take a look at the graph at the lower left. If you look at the upper left, you have an output spectrum, and each output wavelength is at each output waveguide. Each output waveguide corresponds to a different color in the plot shown below. Each peak corresponds to the AWG response at each output waveguide, and we simulated the throughput of each AWG response. And with this information of AWG response, we with this information, given the wavelength, each different wavelength has a different peak and corresponds to a different output waveguide. So right here is the efficiency, and in the x-axis you have the wavelength. With this information, we constructed a calibration matrix from the AWG response as a square matrix. The reason why we did this is so that way we could extract the spectrum by performing operations such as matrix inverse. And the way this works is we can compute the observed power by multiplying the AWG response by the source spectrum through matrix multiplication using the equation below. So if you look here, you have A as the AWG response matrix, S as the source spectrum, and P as the observed power. And what we're trying to do is find the source spectrum, extract the source spectrum S given the observed power and the AWG response matrix. So to start with, we used a low resolution spectrograph at 1000 resolving power. So 1000 resolving power, we started off by using an original test spectrum for carbon monoxide. Then we extracted the source spectrum using simple matrix inverse. Given the matrix equation here with AWG response and the source spectrum, and over here the observed power, we were able to perform matrix inverse. So in the equation below, the matrix inverse here actually corresponds to the efficiency matrix. So given that and the observed power, we're able to find and extract the spectrum. So if you look at the graph on the right, you will see that given the x-axis is wavelength and the y-axis is normalized power, the green curve corresponds to the original spectrum, while the blue curve corresponds to the original spectrum at 1000 resolving power that hasn't passed through the AWG. And the red curve corresponds to the extracted spectrum after passing through the AWG. So if you look carefully, you have the green curve for the original spectrum, the blue curve, which is the original spectrum on 1000 resolving power, and the red curve, which is the extracted spectrum after passing through the AWG. The red curve aligns with the blue curve. The extracted spectrum aligns with the original spectrum at the same resolving power, which shows that for a low resolution spectrograph, you're able to very easily extract the spectrum. Next, we tested this for a high resolution spectrograph at 12,000 resolving power. It was the same procedure as the 1000 resolving power. We simulated the throughput and extracted the spectrum. We extracted the spectrum with matrix inverse. Given the original spectrum on the top right, we were able to extract the spectrum. The same, if you look at the graph at the bottom right, it's the same type of graph as the previous slide, where the green curve is the original spectrum and the blue one is the same spectrum at 12,000 resolving power. The red curve is the one with the extracted spectrum after passing through the AWG. However, this contains significant noise. So that is the main issue. This contains significant noise, and the instability arises because we have a nilpost problem with the matrix inverse operation for the AWG response matrix. So this requires a solution, and the solution we used to correct this was regularization. So we applied multiple methods to try to reduce the noise and reduce the instability. Since the original extracted spectrum contained significant noise, we applied methods such as the Tikhonov regularization. Now, I can't emphasize enough how much I had to spend. I spent 2 weeks to try to study the math and the applications of Tikhonov regularization on machine learning, and how to reduce noise and extract a spectrum using Tikhonov regularization. So let me describe how this works. So the way this works is you're computing a norm of this and using this, calculating and minimizing the expression over here. A corresponds to the AWG response matrix, and B is the observed power. And lambda here is a regularization factor. So you have to adjust the regularization factor to decrease the noise as much as possible. And what we're trying to do is minimize this expression to find the optimal X. And with the right regularization factor, we're able to reduce the noise. After applying the Tikhonov regularization, what you'll see in the top left is the noise is reduced, the instability is reduced. However, it needed altering the regularization factor to reduce the noise even more. And we even tried 3 different solvers in SciPy, which is a function in Python, a solver in Python, non-negative least squares regression, linear least squares regression, and the QR method of optimization. We tried applying all those three, and while they did remove all instability, remove all noise, if you look at the bottom left right here, there's still a spectral shift. So the green curve corresponding to the original spectrum and the red one corresponding to the extracted spectrum, it's not aligned with the original spectrum. So here we're going to talk about the spectral shifts in more detail. If you look at the upper right, the blue curve corresponding to the original spectrum at this resolving power of 12,000 and the red curve corresponding to the extracted spectrum, there is a spectral shift between the extracted spectrum and the original spectrum. More interestingly, that we notice the extracted spectrum and the original spectrum, that shift increases with increasing wavelength. So as we increase the wavelength, the the shifts actually increase. They monotonically increase in a linear progression. So since the shifts increase in a monotonic linear progression, what we notice is we need to apply a linear correction to fix the shift. And that's what you will see in the bottom right-hand corner right here, that when we applied a linear correction, we were able to fix this shift. However, we still don't know what the cause of the spectral shift is. That is still a mystery. What physically is the cause of the spectral shift is still a mystery. Once we can find that out, we can more easily extract the spectra of planets and stars and characterize exoplanets and show how efficiently these compact spectrographs are in detecting, characterizing, and extracting spectra of these exoplanets. So in summary, to recap, astrophotonics deals with guiding light through the waveguides to extract spectra, and the light propagates through waveguides similar to tonal internal reflection. It replaces bulk optic systems with photonic chips for exoplanet characterization, and using AWGs as the main components for spectroscopy is the most promising method for extracting spectra of exoplanets in astrophotonics. We were able to extract spectra for 1,000 to 12,000 resolving power AWGs by calibrating the AWG response matrix into a square matrix to perform operations such as a simple matrix inverse. However, for a 12,000 resolving power AWG, the original spectrum had lots of instability, so we applied regularization methods to remove all instability from the extracted spectrum, but there was still a spectral shift between the extracted and the original spectrum, so we applied a linear correction to correct the spectral shift, but that still has an unknown cause. We don't know what the cause of the spectral shift is, and once we do, we can continue to hopefully extract the spectra of planets and stars. So future directions, what we aim to do in the future is to find the cause of the spectral shift, to computationally double the resolving power of a high resolution AWG. And what I mean by this is for a high resolution AWG of 12,000 resolving power, I already was able to start to computationally using software, double the resolving power to 24,000, but we need to test this on the high resolution WG and see how efficient it is. And from there, what we can do is, if all this succeeds, if all this works, we can extract the spectra of planets and stars and extract the spectrum with the higher resolution AWG spectrograph. And hopefully what we also aim to do is validate our methods in the lab with AWG hardware. We weren't easily able to do this before because parts were delayed due to shipping and due to delayed shipping and also due to COVID. We couldn't easily validate all our methods in the lab using the AWG hardware. But if we can do so, we can more so validate our methods and easily extract the spectra of the planets and stars and show how efficient these compact spectrographs are. Thank you, and feel free to ask any questions.